In this project, we will simulate the passage of external airflow on Santa Claus carriage. In this project, the external airflow around the Santa's carriage has been investigated. The airflow enters the computational domain with the velocity of 30 meters per second and passes over the carriage. Realizable K-epsilon model with the standard wall functions are exploited to solve the turbulent flow equations. The geometry of this project is designed in ANSYS design modeler software and consists of a rectangular computational domain with a carriage in the middle of it. Also, the geometry of the present project is meshed in ANSYS meshing software, and the mesh type used for this geometry is unstructured, and the element number is equal to 1,344,854. Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, a new window will appear showing you the domain extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. Now there are several assumptions taken into account for this project. First, the type of our solver is defined to be pressure-based since we are dealing with incompressible flows. As for the velocity formulation, we have selected the absolute format. And as for the time study, we have selected a steady time study since we didn't want our results to be a function of time. In present project, realizable K-epsilon model has been used to solve the turbulent flow equation since it is more accurate than the standard K-epsilon model. Now, if you click on the inlet boundary, you can see that the type of this boundary is defined to be velocity inlet. By clicking on Edit button, a new window will appear in which you can change the settings for this boundary. Now, in the appeared window in front of the velocity magnitude section, you can see the value of velocity entering this boundary is equal to 30 meters per second. As for the outlet boundary, you can see that the type of this boundary is defined to be pressure outlet. In the settings window in front of the gauge pressure, you can see that the value of 0 is set in here, which means that our airflow will exit our computational domain to the atmosphere. Now for this wall boundary, under the momentum tab, you can see that the stationary wall motion along with no slip shear condition are defined for this wall. Now for this wall boundary, under the momentum tab, you can see that the stationary wall motion along with no slip shear condition are defined for this wall. Now for this wall boundary, under the momentum tab, you can see that the stationary wall motion along with no slip shear condition are defined for this wall. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling, which in this project is set to be coupled. Also, you can see that the spatial discretization methods are shown in this window. Now, the coupled scheme is kind of an algorithm in which pressure and velocity equations are solved together in tandem. This algorithm may be more accurate and exact in comparison to iterative algorithm, but it may take more computational time in comparison to algorithms like simple or simple C or other algorithms. After double-clicking on the Controls button, in the middle section of the software window, you can see that new part will appear. In the Appear part, you can see under relaxation factors for different parameters. Now these values are set here by the software automatically. You can change these values, which are between 0 and 1, by yourself for different projects you do. But it is highly recommended that you do not do that, since it may result in divergence. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the zero, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. For example, in this report, you can see that a report has been defined. By double-clicking on this report, you can see that we have defined a drag coefficient report on the Santa Claus carriage surface. After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. After double-clicking on the Run Calculations button in the Appeared section under the Parameters part, by just defining the number of iterations and then clicking on Calculate button, the software will start the simulation process. Now, in order to extract different contours, we right-click on Contours button and then select New. After the appearance of the new window, under the Contours of section, you can select your desired variable, which in this slide you can see that we have selected the pressure. After that, underneath it, in the Surfaces section, you can select your desired surface where you want to see your contour. For example, in this slide we are going to see the pressure contour on the Santa Claus carriage outer surface. Now in this slide you can easily see the pressure distribution on the carriage outer surface. Also you can see that in the front section of the carriage the pressure value has increased, which is due to the formation of a stagnation point on the front section. Also, in order to extract another contour, all we have to do is to change the previous variable into a new one. After that, just like the previous slide, by selecting your desired surface and then clicking on Save or Display button, the software will show you the contour. And now in this slide, you can easily see the velocity distribution inside our computational domain and passing over the Santa's carriage. Now, as previously was mentioned about the definition of a drag report on the carriage surface, here, by expanding the report plot under the monitor section and double-clicking on the drag report, in the appeared window, by clicking on plot button, the software will show you the changes of drag coefficient in terms of number of iterations. Now in this drag coefficient diagram, we can see that the values of drag coefficients have fluctuated a lot. Now in order to decrease and lower this fluctuation, you can reduce and lower the values of under relaxation factors. For example, if you compare this slide with the previous slide about under relaxation, you can see here that we have decreased the under relaxation factors for pressure, momentum, and body forces. Now after changing those under relaxation factors, if you let the Fluent software to continue its simulation process for a few more iterations, and then plotting the drag coefficient plot, you can see that the value of fluctuations has decreased. Now, as was mentioned in previous slide about decreasing the fluctuation in the values of drag coefficient, here you can see the new diagram of drag coefficient after we have changed the values of under relaxation factors for parameters like pressure, momentum, and body force. Now if you compare this new diagram with the previous one, you can easily observe that in this new one the fluctuation has decreased. Also, another prominent factor in this project is the value of y plus on the carriage surface. Now in this slide you can see the maximum, average, and minimum values of this y plus on the carriage surface. Now considering that we have used the standard vol function in this project, the maximum value of vol y plus is in the acceptable range. Now in order to compute the values of y plus, all you have to do is to right click on report definitions, then go over new, and then go over surface report and select facet maximum or facet minimum or facet average. Then in the appeared window under the field variable, we select turbulence, and underneath it we select vol y plus. After that, under the surfaces section, we select Santa Claus carriage and then click on compute. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.